symbol is popping up. Okay, so let's go. So next speaker is Horia Cornean, so from Aalborg University, and he's going to speak about, as you see, well, let me look for the title, extending the BulkEdge Correspondence to positive temperatures. So,
okay. Thank you very much for the introduction, and it's a pleasure to give this talk. I mean, it's a pity that we cannot be physically present in Beirut, but maybe some other time. So I want to stress from the beginning that this is a joint work with two good friends, Massimo Moscolari, who until some time ago was in Aalborg, but then he deserted and joined forces with Stefan Teufel. And they are both now in Tübingen. Actually, I don't really know where they are. I mean, with this Corona times, it's not very clear. Okay. And I also want to express some very special thanks to a bunch of other Italian guys, Gianluca Panatti, Domenico Monaco, Giovanna Marcelli, Marcello Porta, and Giuseppe De Nitis. All of them had an important role in making me understand this problem. And, you know, probably the easiest thing to do in order to understand something is either to give a course on it or to write a paper. Okay, so again, the title is about BulkEdge correspondence at positive temperature. And I will try to do my best in order to explain what the problem is. And I mean, I will not have time to do any proofs, but I don't think that anybody will be very unhappy about that. So I want to mention also that this is a very well-studied problem. And the list of people who contributed to this is kind of very long. And I also put, I only put a very short list of people with whom I actually discussed. So Jean Bélissard, Hermann Schulz-Balles, Emile Prodan. And I put the name of Alexis Drouot in red because, his way of looking at the problem kind of inspired me quite a lot. And while the first three look at the problem from a point of view of topological or non-commutative geometry and K-theory, Alexis is doing some more functional analytic approach, and in some way, what we do here is well, resembles a little bit that way. Okay, so let me go directly to show you a picture and introduce some notation and explain what the physical setting is. Can you see my pointer here? Okay, good. So the configuration space will either be the whole two-dimensional plane, so R2, or half of it. So this capital E means that only so the y coordinate can be larger or equal than 0. And here we have a wall, which at some point we will either talk about Dirichlet boundary conditions or Neumann boundary conditions. It's not really important here. Okay, and there will be some other quantities which will play a pretty important role. So there is this fundamental cell, which I call omega 1. So it's a unit square. And then if I have L copies, there will be omega L. So L typically will be an integer in my talk. And when L is infinity, then it will be an infinite strip, and then that would be omega infinity. Then, well, this is about Schrödinger operators with magnetic fields. So let me show you what will be the two main actors in this show. So H infinity of epsilon, this would be an operator defined on the whole space. And this is usual magnetic Schrödinger operator, where we could have some periodic magnetic potential A. So you can see that this guy is Z2 periodic, while this A0 corresponds to a magnetic field, or generates a magnetic field of strength 1, which is perpendicular to the plane. And here we choose to work with the Landau gauge. So A0, it only depends on the second variable, is independent on the first one, which makes that the corresponding operator is still periodic with respect to the x1 direction. And yeah, for simplicity, let's consider that all these coefficients entering here are bounded and even smooth. So there are no troubles with the domain and so on. The only kind of singularity, if we can call it like that, is coming from the fact that we work with a constant magnetic field. And we know that constant magnetic field is a pretty serious perturbation for the Laplacian. So anyway, you see that this epsilon here will be kind of a small number. And it indicates, and we perturb an already existing constant magnetic field in the system. And so this B0 in principle should be kind of a large number if we want to be sure that some non-trivial topological effects will appear in the system. Okay, and when I put H subscript E, that's exactly the same operator, but with some boundary conditions. So I think somebody is not muted. Is that just me who's hearing this? Well, I'm not the one. Okay, good, great. So let's go further and introduce some new notation. So I'm introducing this function f of x, which is kind of a generic guy. It's not really important what happens in the negative axis. You see here, so these red intervals, they are representing the possible spectrum of the full operator, so H infinity. And it might have some gaps, it might not have. And so this capital F is supposed to be a function which is smooth and goes sufficiently fast at infinity. Well, in what we are going to use, we will work with this Fermi-Dirac distribution, which has exponential decay at infinity. And here, beta is thought to be the inverse temperature, and mu is the chemical potential. And of course, we can define already the operator density, or the density operator, and simply given by the functional calculus. So I take this function f, and I apply it on H infinity of epsilon. Yeah? So that's the particle density particle operator. And let me state a few very well known facts. So this density operator will have integral kernel, which, so just think about its Schwarz integral kernel, and it will be kind of a nice function, very strongly localized as a function of, so if I had written here x and x prime, then this is an object which is very strongly localized in the difference, so around the diagonal. And if I put x and x prime to be equal to each other, it generates also a C infinity function, which is not just C infinity, but also it's Z2 periodic. which is maybe, I mean, for people who work in this field is definitely not a surprise. Well, this is related to the fact that we have gauge covariance of the magnetic operator. So the magnetic operator is not periodic in both directions, but such integral kernels, and so the diagonal of such integral kernels is always periodic. Okay, and then we can define the actual density. It's kind of a local trace. So you see, I multiply my operator with the indicator function of the elementary cell, and it turns out that this is a trace class operator, and its trace can be computed as the integral of its the diagonal of its integral kernel, and the resulting function, of course, is non-negative, and it's smooth as a function of the external magnetic field. This is also kind of a very well-known fact, well, I just stated here without other extra remarks. Now, this is probably not so clear. So the next thing here, I introduce kind of a funny operator, and I will spend a little bit to explain kind of why this is related to a current operator. So here we see a commutator between the edge Hamiltonian and the x1 coordinate seen as a multiplication operator. So this is kind of the velocity operator in the direction x1. And then here, this is multiplied with the operator defined by taking f prime of he. So you differentiate the function capital F, and you get f prime. And well, this guy here, the first term, is constructed using the edge Hamiltonian, while the second term is constructed with the bulk Hamiltonian. So, I mean, these are not very nice operators, but because they are applied on some smoothing operators, so just think about that as some very nice integral kernels, which are defining integral, so bounded operators. And then everything is multiplied with the indicator function of the infinite strip. So if I should go back to, oh, no, this was not very good. So I'll try to go back to the picture. So what's going on here? So omega infinity is this strip. So due to the strip omega infinity, we have localization in the x1 direction. And it turns out that the difference between these two operators is also localizing in the x2 direction, because when we go far away from the boundary, the edge operator starts resembling quite a lot with the bulk operator. So once again, this difference is localized in the x2 direction, and multiplying with the indicator function of omega infinity is also localizing in the x1 direction. So that's why it's not so surprising that the operator itself is trace class. And the same thing is true for the second operator I2. Again, here we have a commutator of the bulk operator with the x1 coordinate, and multiplied with f prime. And then this operator is also multiplied with x2, but because everything is restricted to the fundamental cell, x2 is just a bounded object here, so there's no problem with it. And it turns out that I2 is also a trace class operator. Okay, so I can now state the main result, which is nothing but kind of an identity, which says the following thing. So if we differentiate the density as a function of epsilon, so remember that this was the density of particles, as a function of this small change in the magnetic field, on the constant magnetic field. So if we differentiate that, and I put it epsilon to be 0, then this can be written as the difference between two traces. The trace of I1 minus trace of I2. Now, you see here a more detailed expression, which is saying more or less what the two traces are. And I chose to work with two different colors. This reddish color indicates everything which happens in the bulk. So you see that all these operators are operators kind of living in the bulk, and also rho f was a bulk quantity. While here on the right-hand side, we have something which lives in the half plane. And so this P1, maybe I shouldn't have called it P1. It's better called V1, because it's what comes out by taking the commutator between either h infinity or he with x1. Yeah, so it's the first component of the velocity operator. Okay, so so this is basically the whole result. But now let me try to explain what on earth this has to do with the bulk boundary, and to explain a little bit more about the physics behind. So this identity, as is written here, is valid for all temperatures, or in particular, is valid for every Schwarz function f with the right properties. And now, what happens if our operator h infinity has a gap in the spectrum? Okay, so let's look at that situation, and this is the classical situation in this quantum Hall effect setting. Let's assume that our operator h infinity has a separated spectral island, which kind of shows, so the corresponding projection to the sigma 0 would be the Fermi energy, or the Fermi projection, sorry. And let's assume that the chemical potential lies inside the gap between sigma 0 and the rest. And by doing that, we see that when the temperature gets lower and lower, that means when beta goes to infinity, then the profile of this Fermi-Dirac distribution function will start looking like something which is very close to B1 for x less than mu, and then something which is very close to B0 for x larger than mu. Of course, we have pointwise convergence and so on, but if we restrict our x to be to a small, outside a small interval around mu, we have, of course, uniform convergence in every possible topology you can imagine. And so let me formulate this as a lemma. So when we try to look what happens if instead of just one function f, we have a sum of two functions. Of course, we have linearity, because rho is a linear expression in f. And remember that rho was just a local trace of f of h infinity. And it also turns out that its derivative with respect to the magnetic field is kind of continuous in some semi-norm topologies of f. And yeah, so I can, so there is some sufficiently high number n, and a constant Cn, such that rho f prime can be dominated by a number of derivatives of f multiplied with some growth at infinity. So you can see that all these things can be formulated also for kind of larger classes of functions. We don't really need exponential decay okay. Okay, so what happens now when we take the temperature to 0 or beta to infinity? What happens with this formula? Well, it's not so surprising. So let's look here. Now I pick up some function f0. So f0 is not, well, I mean, it will, so that the result will be kind of independent of f0. And f0 well, has two important properties. It is equal to 1 on sigma 0. Let's say this is the energies up to the Fermi level. So f0 is equal to 1 here, and then it smoothly goes to 0 in the gap. So outside the gap, here on the right hand side, f0 is equal to 0. So this makes that when we differentiate with respect to x, so f0 prime, this will be a compactly supported function inside the gap. Okay, and so this f0, as I said, is a fixed function, but arbitrary up to these two properties. Okay, so we have a proposition which tells us that if I take the temperature, so if I make beta to be larger and larger on rho prime of f beta mu, then it will converge exponentially fast to the same quantity in which I replace f beta mu with such f0. Yeah. So that also means that the limit is kind of independent of f0 because it has to be. And we also note that if we take f0 of h infinity, so the function f0 on h infinity is exactly the Fermi projection. Of course, it's independent of f0. Okay, so what happens with our formula if instead of f beta mu, I put f0? Well, it gets...
Horia, may I ask you just a quick question? So this is well, it requires exactly that mu is in the gap. So you have, so the errors depend on the distance between mu and the spectrum, I guess.
Absolutely, absolutely, yes. This, okay. I mean, there are many things put under the rug here. Okay. But it's good that you keep an eye on me because I mean there are several things where I already cheated. So
okay.
Yeah. So exactly as you say, this limit is not uniform in
mu.
In the gap. So these two constants are very strongly depending on the gap.
Both constants. I mean.
Yeah. And also, if we don't have a gap, then we have a problem. And that's why I don't want to talk at this stage about the disordered case where you could have some. I mean, you could have a mobility gap in the sense that this chemical potential could be in a localization regime, but I don't want to say anything about that case because, I mean, to be honest, we don't really know how to deal with that. Okay, good. Not yet. Maybe next time. Okay, so let me tell you what happens now with the formula when we take the temperature to 0 or beta to infinity. So you can see that it gets a bit shorter. And well, I mean, on the left-hand side, of course, that we get this limit, which we know it exists. And on the right-hand side, it's just the first term we had before, and I'm not sure that I can find the formula out. Yes. So look, I mean, suddenly this guy is not there anymore because when I put f0 instead of f here, f0 prime is supported in the gap where there is no spectrum for h infinity. So this is identically 0. It's only crucial to have it here where f is general and it sees some spectrum of h infinity. Okay, so that means that now we have something here on the left-hand side, which is something living clearly in the bulk. So this is a purely bulk quantity, which doesn't know anything about boundaries or the fact that I cut the space in two. And here on the right, we have something which is manifestly depending on a operator defined with a boundary condition. And here you see that this is again like the well, it's not really a current operator. It's like, so if there is no prime there, then this would be exactly the kind of a current. And due to the prime, it's just think about like it's a conductivity, because this is kind of a current differentiated with respect to some chemical potential. So it's not such a big surprise that both these quantities here are very much related to the conductivity, to the whole conductivity. And that's exactly what I want to stress now. Okay, so what is this guy? What is the derivative of the density of particles with respect to the external magnetic field? And so, I mean, everyone who had some physics courses in their youth, there is a thermodynamic identity which says that if you differentiate the density with respect to the magnetic field, then this is the same as differentiating the magnetization with respect to the chemical potential, something like that, up to a sign. Now, from this very nice talk from this morning about Maxwell equations, we know that I mean the magnetization. So when you differentiate the magnetization with respect to the coordinate x, so think about that you put some electric field in the system, and that will create a change in a local chemical potential. So differentiating magnetization with respect to the chemical potential is like taking its curl. Okay, I mean that's kind of a long shot, but and the curl of the magnetization has something to do with the curl, and so that's why I mean. Actually, I will tell you about something which is called the Strata Formula. And Mr. Strata, actually, he has a very nice, very short paper in which, I mean, half a page or something like that, in which he says, oh, this must be trivial because everybody knows it. Okay. And so we, I mean, together with Domenico Monaco and Massimo Moscolari, we worked quite a bit on this problem, and we have a kind of very direct proof of the fact that when you differentiate this density with respect to external electric field, the magnetic field, sorry, then up to some constants, you get something which is called the Chern number of the Fermi projection. And well, actually, it's not. I cannot really say it is really the Chern number, because I mean pi zero is not necessarily periodic, but it's something with which people used to call Chern marker or Chern character or something like that. But anyway, it's an integer, and so this is known as the Strata formula. Well. As I said, Strata derived it in a different way. So he said, okay, I mean this rho prime must be conductivity, and then he proved. Actually, I think he was the first one proving the fact that whole conductivity must be an integer, because he looked. I mean, he used an older paper by Vanier. And so he looked at a particular operator, so not at the continuous Schrödinger operator, but at Hofstadter model. And then he used some very nice tricks of Vanier to say that, I mean, for that particular model, you could compute explicitly this derivative for some values of the electric field. And they were all constant. Equal to some integers. So that's why he kind of postulated that this must be true for every model. Okay, well, so what? Now, let me show what usually is known as the BulkEdge correspondence. So the BulkEdge correspondence says that something here, which is completely expressed in terms of a half operator, so defined on some cut space, has some non-zero conductivity, even though we started with the insulator. So remember that the operator we started with at zero temperature was an operator with a gap, and the chemical potential was inside the gap, and we don't really expect that it leads any current in the kind of direct current, because the whole current is a transverse current. That's a completely different thing. But here you see, now I took my insulator, I cut it in half, and then I see that there is some current going on parallel to the edge. Because remember that this is V1, it's kind of the velocity operator parallel to the edge. So we have conduction there, and the conductivity, or kind of the direct conductivity along the edge, is exactly the same as whole conductivity in the bulk. And this is kind of a nice identity. And I must confess that I've heard many talks about BulkEdge correspondence in my career. And it took me probably like 15 years to understand what that was. So I'm very happy. I'm very happy. I hope that at least somebody in the audience will also have a revelation today. Okay, now I think that I have like 15 minutes left, so that's okay. So I will try to give an alternative derivation of the fact that the right-hand side is an integer. Yeah, I mean, of course, I mean, if anybody knows that, I mean, that this chair number is an integer, that's fine. But because we should also learn some nice things today about this, I will try to convince you that one can give a direct proof for the fact that this right-hand side is an integer. And let's look how we can do that. Okay. So for that, I will need to introduce some nasty notation, and I will spend a couple of minutes to explain what all this stuff means. So again, look, I mean, this is our old friend, the edge Hamiltonian. So this is nothing changed. This round A is periodic, is nice. This part here is not periodic in the x2 direction, but is periodic in the x1 direction. So we still have some periodicity left for the edge Hamiltonian. And this will play a major role in what follows. Now, up to some Bloch, Floquet, Gill, van Zach, I don't know which name you prefer, transformation, we can show that the edge Hamiltonian is unitarily equivalent with the direct integral of a fiber operator. So you see that I have two types of x's here, one with an underscore and one without an underscore. So this x1 here lives only in the interval between -1/2 and 1/2, which is the elementary cell for our problem. You can also think about 0, 1, it's the same. While x2 is only from 0 to infinity. So this is so the fiber here is not defined on a bounded domain, as is usually the case in this Floquet theory, or when one deals with the periodic operators in all directions. Okay, so to shorten the notation, I call this this guy here HK1 is depending parametrically on the K1 variable. So K1 is the quasi-momentum, and because I put the 2 pi's inside here, so there is a 2 pi times k1. That's why for me the Brillouin zone is exactly the same as the elementary cell. Otherwise, I mean, I should have written here from minus pi to pi, and there should have been just k1 there. Okay, so k1 is a parameter, it's a real parameter going from minus 1/2 to 1/2 in my case. And what is the domain? The domain is L2, I mean, it's densely defined on L2 of omega infinity, and omega infinity is the infinite strip from 0 to infinity in the x2 direction, and we have periodic boundary conditions on the vertical lines. So periodic means that a function which lives in the domain of h should have equal values at both minus 1/2 and 1/2. Okay, good. So what? What about the spectrum of such a fiber? Now, for people who are used to periodic operators, usually these guys, these fiber operators have pure discrete spectrum. The resolvent is compact and so on, but this is not the case here because so the HK1 is defined on an infinite, semi-infinite strip. So each fiber actually has a lot of essential spectrum for every value of k. So, and what is the essential spectrum of this operator is exactly the, let's say, the bulk spectrum. And it's not so difficult to understand why this is true, because if you go very far away from the boundary due to the ellipticity of these operators, you don't really see the boundary anymore. So you expect that anyway, the essential spectrum, or by using some while sequence arguments, the essential spectrum will be given by the spectrum of H infinity. And that's exactly what happens. But on top of that, there could be some supplementary spectrum, like discrete spectrum. And you see these blue dots here, they indicate some possibly, some possible eigenvalues, discrete eigenvalues. And well, we have here two of them, lambda 3 and lambda 4, which might be there or might not be there. But actually, one of the very nice things about this problem is that there will always be at least one edge state, and it will cover the gap. But okay, let me take it slowly. Okay, anyway, so this blue eigenvalues, when k1 varies, they move, and they form some absolutely continuous bands, and we call them edge states for well, it's not H infinity, it's edge state for HE. Yeah, so it's not the H infinity here. But anyway, so we can write down a nice identity. So you remember this current, or let's say conductivity operator, if I can call it like that. So it, well, it's a periodic operator in the x1 direction, because you see there is a commutator here. So we can write it as a in a fiber form. And it turns out that the fiber operator corresponding to this guy is nothing but the derivative with respect to k1 of the fiber operator times f0 prime of hk1. Yeah, so that's gonna, I mean, that's what usually happens. Taking commutators with the x in the k representation means taking derivatives with respect to the quasi-moment. So it's not a big surprise. Okay, but now remember that we were supposed to take some local trace of this guy. Now, taking the local trace of a direct integral amounts to integrate with respect to k1 the trace of whatever is here in the direct integral. And that's exactly what happens. And let me jump directly to the final formula. So the trace So this is a big error here because I forgot to put indicator function. Okay, maybe I should put it now to show you that I have a very nice tablet here, but pencil is not very good. Okay, so this is, yeah, okay. Now it's trace class and it's fine. So the right-hand side of our formula, which should be an integer, can be now written as a relatively simple integral involving derivatives with respect to k1 of the edge states multiplied with f0 prime of the same edge state. And well, okay, well, there is some work to show that these lambda n's actually are some smooth objects as a function of k. That's not a big problem because k1 is one-dimensional, and we have, I mean, we know that in the one-dimensional case, Rayleigh's theorem allows us to choose some functions which are quite regular, actually real analytic. And especially that you remember maybe that this f0 prime is supported in the old gap. So we don't risk to be too close to the essential spectrum where these lambda n's actually will end up. Okay, so what can we say more about? Okay, so I hope that, yeah. So actually we can perform the integral because this is nothing but, I mean, this is a total derivative, and we can write this as the sum of some differences, which says that we have to look at f0 at where the eigenvalue ends up at the end of the Brillouin zone, which is 1/2, minus the place where the eigenvalue started. And remember that we have to look at these differences only if lambda n is in the support of f0 prime. And okay, maybe I should not insist too much on this, but you remember that our formula was also independent on which function we choose. And now if I take formally just some 1 minus Heaviside function, this is exactly telling me that well, the Chen number, or this derivative rho prime at 0, is a sum of some things which can either be 0, 1, and -1. And it follows how many eigenvalues cross from one side to the other. So you remember that, okay, so this x here, I can choose it to be arbitrary because, well, this f0 is also arbitrary. And so it means that if the left-hand side is not 0, then we will always have at least one eigenvalue which crosses from one side to the other, more than the eigenvalues with cross on the other side. So I could have some eigenvalues coming from here and end up on the right-hand side, and some other eigenvalues which start here and end up there. But in any case, the gap is necessarily gone. There is no gap there anymore for the edge case. And so if the Chen number of the unperturbed Fermi projection is not 0, then necessarily when I put the edge Hamiltonian will have spectrum inside the old gap. And so the old gap is disappearing. And so this last discussion about eigenvalues crossing from, so let's say getting out of sigma 0 and ending up in the other side, or so starting from the upper spectrum of the bulk and ending up in the lower sigma 0. So this is what physicists usually call bulk boundary correspondence, and I'm really happy to have understood that. Okay, so let me go directly to to conclusions and some questions which I asked myself. So the first thing is, can we say anything about the survival of the gap if the Chern number of the Fermi projection is 0? Let's say if we have in a topological if we are in a topologically trivial case. I mean, are there examples of perturbations which close the gap, for example? It's not clear. At least I'm not aware of them. Now, in such a, let's say, trivial case, that is, if we have time reversal symmetry, that means that the operator we start with is real. Then one can prove very generally that we have this symmetry for the density operator. So if we differentiate respect to epsilon, then we get 0. Okay, and it doesn't need a gap for that. But the question is now, can we say maybe something about the second order derivative of this? Like, is there above boundary correspondence for the magnetic susceptibility? That's what it is expected to get out of the second derivative of the density. That's the susceptibility. And okay, now another thing which could be added to this problem is to add random potentials, or to put some even random irregularities in the boundary. The result would be essentially the same. The only difference is that one has to take the expectation. So, I mean, of course, there is need for some sort of ergodicity of the system. And if this ergodicity holds, then the formulas which I wrote before are still true, with the price of having to take an expectation over the random variables. And that's pretty much it. And I also have a nice thank you here.
Thank you very much, Horia.
You're welcome.
So, questions? Check also participants if any more. Start a question. So we learn very a lot. So here a question is coming from Iman. So go ahead.
Thanks, Horia. So it's not really a question, just a comment that I look at your operator H infinity of epsilon, and I see like you are preparing to differentiate it with respect to the magnetic potential, because you look at the term B0 plus epsilon. So just in my memory is that also I remember a formula that says differentiation with respect to magnetic potential yields the current in the physics literature. So
is this in my talk?
Yeah, it's not in yours. I don't know. I mean,
okay, so it's not a formula I wrote. Okay, so can you repeat? So you say that if you differentiate?
So I'm saying about your operator H infinity of epsilon.
Yeah.
So you put epsilon as B0 plus epsilon.
Is this thing? Yes, B0 plus epsilon. Yes.
Yeah. And then you differentiate with respect to epsilon.
Yes.
So it's like you take the derivative with respect to the magnetic potential.
Yes.
So in other contexts, I remember I saw also a formula, but not in your paper, in other papers. I remember maybe a paper by Soren Fournier, who compute the current by differentiating the operator with respect to the magnetic potential. So maybe this.
Well, I mean, it's most probably a standard thing to do. I mean, it's also coming from thermodynamics, more or less. No, I mean, so if you differentiate, actually, CERN was looking at magnetization or susceptibility or something like that. So he was differentiating magnetization respect to the magnetic field, and of course, this thermodynamic identity, which is more or less trivial.
Yeah, but they don't see the edge quantities because they don't have boundaries.
Ah, they don't have boundaries. No. So they work for bulk operators.
Yeah.
Yeah.
So that was my comment only.
Well, I mean, Alex is dual, so he doesn't have magnetic field either. So he only works with purely periodic operators. And what he's doing there, I mean, he shows by brute force that the Chen number of the Fermi projection can be written as something involving boundaries. So it's not. So what we're doing here, we start with this more general identity which holds for every temperature, and then when you take the temperature to 0 and you have a gap, then you get so that's the major difference. Yes.
So actually, I'm interested in other problems where it's interesting to find some kind of edge currents, let's say. So that's why I'm happy with the formulas I see in your talk. I mean,
me too. I mean, I can imagine.
Horia, a simple question. Do I understand right that the argument with crossing the eigenvalues, what really matters is the value at the right and left edge of the Brillouin zone, that the form of the dispersion function is irrelevant?
It is irrelevant, yes, but so this argument says that if the Chern number is different from 0, then there is at least one such edge state which comes out of, let's say, sigma 0 and ends up on the other side. Yeah. So I mean, just think about a very well-known model. Let's take just the usual lambda operator with constant magnetic field in 2 dimensions. So exactly the same model, but v is equal to 0 in this case. Okay. And the spectrum of this guy would be just the Landau eigenvalues. Yeah, so it would be B0, 3B0, 5B0, and so on. And you have gaps and so on. Now, if you put the boundary, if you only look at half of the space, then you can do a lot of analysis. And so what happens is that you have this edge state, which actually starts from so with Dirichlet boundary conditions, the edge state starts from, let's say, the upper Landau level and goes down to the lower one, and all the gaps are filled. Yeah, so the edge Hamiltonian only has absolutely continuous spectrum, and it's filled by exactly one eigenvalue. So in that case, well, this is kind of a very nice thing, and this confirms that the Chern number of each Landau projection is equal to 1. Yeah?
That's clear. What I have rather in mind was that in some models you can have dispersion functions where the eigenvalues go to and fro, so it can cross the same point to the one side to the other. But what really matters, if I understand you properly, is the beginning and the end, nothing more.
Yeah, I mean, it's something you can kind of conclude from this formula that at least one eigenvalue will definitely cross. It's not coming back, because I mean the gap could also disappear because you just have some eigenvalues which at some point cross each other, but they don't go from one side to the other. They just they go back. That's also a possibility.
Okay, thanks.
Okay, so any more questions, comments? One? Yes, who's speaking?
Yeah, it's Nicola from.
Okay, so I didn't see. Go ahead.
Yeah, I was just wondering, perhaps you said it and I just missed it, or is there an expectation from the physics literature on the last open question you say about the susceptibility in the time reversal case, time reversal invariant case?
I have to admit that I looked for it on Google and I didn't find anything.
Okay, so that doesn't exclude that there is in a more subtle.
Too lazy.
mean, you see, one of the big things which happened for me working on this is that I didn't know that many other people work on precisely the same problem, but using some completely different keywords. You know, and I know this Strata formula is called, I know, in many other ways.
Yeah, but I guess if you're looking for results in the physics literature, whatever the key, I think the keyword you wrote is the good one. So if you didn't find anything, maybe there isn't anything. No, but isn't it related to the? Maybe I'm out of my mind, but this Z2 chain insulators or whatever. How is it called? Topological insulators, where you don't have really a net edge current, but you have something more subtle, which is sometimes related not to a Z chain number, but to a Z mod 2.
I think, yeah, I mean, you think about the spin currents and so on.
Yeah, maybe.
But that's Domenico Monaco and Massimo Moscolari who did some work on that, and also Gianluca Panatti and all this. I don't know, should I call it mafia? I don't know, maybe it's not. This group of people.
Okay.
Very talented group of people.
But is there time reversal invariance in this case?
Well, I mean, you could have, of course, time reversal invariance, but in that case, everything is trivial. So,
including the susceptibility, I mean, the second derivative.
No. I mean, nobody looked at that. No. That's really, nobody looked at that. I mean,
okay, right.
these two problems were only for projections and constructing linear functions which obey certain extra conditions. If you have like, well, if the operator is real, so if you have time reversal symmetry, then the question is whether you can construct linear functions which are real. Or something. Yeah, I mean, it's quite a lot of work on that, but not on the susceptibility.
Okay, thanks.
Okay, so any more questions? I don't think so. Okay, so I think now we can stop for a